So we started recording. This is welcome everyone to the course of complex analysis. This is week 9 uh, live session. So as usual, we'll discuss something about what is done in this week, and then we'll solve some exercises, some questions. Okay. Hi. I hope I'm audible and this is recording. The meeting is recording. Let me check. Yeah, it is recording. Okay, so what week is started with? So with the definition of isolated singularity. Isolated singularity. What were this? These were the points of domain where uh, f is maybe not defined, but in a neighborhood, deleted neighborhood means if we leave that point, then it is holomorphic in a neighborhood. Okay, so this is called isolated singularity. So there were three types of singularities which were introduced to us. Introduced to us. This first type is removable singularity. Removable singularity. Uh, as example, I am going to tell you this sin z upon z, something like this. So if you see at 0, it is not a kind of well-defined function. Sin 0 upon 0 is not making sense, right? But you know, as z tends to 0, this limit is equal to 1. Or in other fashion, you can say that sin z has a series expression where series is started with z plus z cube by 3 factorial plus z power 5 by 5, something like that. So you take z common and then cancel out. So 1 plus something you get. Okay. And that is analytic function. So you see that analytic function is extendable. So this function is defined everywhere. If you define, we can extend this function to an analytic function. If you define at 0, it is 0. Okay. So the function we get is what we need. So this is a removable singularity. Second, what is second question? Sorry, second kind of singularity. It is pole. Okay, pole of some order m. These are something like this. For example, easiest way is this: 1 divided by z minus z naught, or pick anything z naught. We can take 0 only. So z minus 0 to the power m. So this function has pole of order m at 0. So know that this function is, uh, if you remove point 0, this is analytic. Okay. This is defined on c minus 0, right? And at 0, it is not well defined. So there is this singularity, and the singularity is called pole of order m. So see, how to check them? How they means they are another question. So we'll think about them. In this. So third kind of singularity is essential singularity. It's essential. Singularity. So these are singularities which are not removable, not pole. Okay. Those which are not removable, not pole, they are essential singularity. Okay, so an example will be something like this: e power 1 by z. And how to check that this is not removable, not pole? So there are some criteria. Removable. In removal case, let Z not be an isolated singularity. Isolated singularity. So if mod of f z is bounded or z belonging to d z not r or some r, okay, or all z belonging to d z not r or some r, then it is removable. So this is theorem, Riemann removals part, okay. Then f, so z not is removable singularity. Okay. Z not is removable. Pencil is not good. Okay. Mhm. This is called Riemann removable singularity. So if in a neighborhood, in a deleted neighborhood, sorry, minus z naught, in a deleted neighborhood, if it bounded, f mod of f is bounded, then it is z naught is removable singularity. Okay. Okay. So what is second criteria? Why when it is not bounded or bounded away means then it is pole. Okay. If it is bounded, then it is removable. If it is not bounded, then it is pole. So uh, it is a pole if or z not z not is pole if limit z tends to z not equal to z naught, then mod of f this is bounded away from zero or it is going to infinity. Okay. Or when I write limit, we should write equal to. Okay. So the poles are clear, removable singularities are clear. Those which are not ha having this bounded and unbounded case scenario, they are essential singularity. So essential singularity, for essential singularity, we also saw one theorem. If you remember this Castle-Rod-TVS stress theorem. This theorem says if Z naught is an essential singularity, then or we can make a statement like this: let and alpha is some complex number. Okay, then there exists sequence Zn converging to Z naught. Okay, so I hope everything is fine. What I was saying is this: if even if a small neighborhood at Z naught, so Z naught is some point in somewhere, the image is dense. So image of this ball, let's say this is D Z naught R epsilon D Z naught epsilon. This is dense. So what this dense image? This means I can write f of d z d z naught epsilon for any epsilon. Okay, this set closure is equal to C. So this is the theorem. Okay, so, right. So we understand three cases: removable singularity, then if it is bounded in a neighborhood, it's deleted neighborhood, not that point is included in our domain. Okay, so wherever we are talking in a neighborhood missing that point. Okay, so pole, in case it is unbounded, then it is pole in a neighborhood, means bounded away, meaning uh, this is the meaning. Okay, and if image is dense inside complex plane, then it is essential singularity. This is Kasarov-Weierstrass stress theorem. And one more thing was done is about Lorentz series expansion and various scenarios when depending on kind of singularity. So we can also write them because they are going to helpful for our exercises. Uh, okay, we can add one phrase. Lorentz series. Uh, how was this defined? Let f from omega. Omega, I'm taking, let's say it is a z naught r1 r2. This is called annulus. This is annulus domain to see the holomorphic function. Then fz is equal to summation an z to z minus z naught to the power n, where n is running from minus infinity to plus infinity, and an belonging to some constant. It is this series is convergent absolutely and uniformly. Yes, and it's equal to f of z. So is convergent absolutely and uniformly and equal to F. Okay, so this series I'm talking on omega with extra. Moreover, these coefficients are some coefficients are some complex number ans where integral or gamma such that this is fz divided by z minus z naught to the power n plus 1 dz. Gamma is some curve or gamma is something, let's say z naught plus r e power it is from 0 to pi. R is between R1 and R2. Okay. So coefficients are also we are able to calculate them. So this is a Lorentz series expansion. Okay. And what happens when Z naught is essential singularity? So when R1 is equal to 0, this annulus becomes deleted neighborhood. Okay. 1 point Z naught is missing, everything is in the R2 disk. Okay, so when Z naught is removable singularity, what happens? Removable singularity, all these an are 0 for every n negative n's. Okay, n negative means n less than 0. So an all n's are 0. When z is pole of order m, then a m, sorry, I should just write an is equal to 0 or every or minus n, I should write pole of order m. All these an's are 0 for n bigger than m. Okay, so there are only finitely many terms with in the series. Most of the negative values or an's are 0. Right. If it is essential singularity, what happens? Essential singularity is the third case. An is not equal to 0 or infinitely many. A minus n is infinitely many, and belonging to positive number. Non-zero, it is non-zero. So the third case from here, you see e power 1 by z. What is the expression? 1 by 1 plus 1 by z plus 1 by z square by 2 factorial plus 1 by z cube by 3 factorial. So we have infinitely negative powers, right? Z to the power negatives. So 0 is essential singularity. 0, this point is essential singularity of essential singularity of e power 1 by z. Right. This is we are just using the arrow remark or observation. Now, all these observations are going to help our exercise solving exercise problems. So I think we have covered almost all of the things. These were some important topics discussed in 4 lectures. Right. If you still have any doubt, you can ask by the the comments because no one of you is attending this session. So these lectures are on YouTube. You're watching them. So you can leave your comments. I will reply. Fine. Now we are going to see some assignment questions. So the first question is to determine type of isolated singularity in each of the following cases. Removables, f is defined on c minus 0. So, and it is defined equal to identity function. It, at 0, we have to check which kind of singularity it is. So what happens if you take unit disk t minus 0? Restricting our f to a neighborhood, deleted neighborhood of that point. F odd f is bounded on the z0 1. This is usually called D, which is unit disk, is bounded on this. Bounded by 1 exactly, so no problem. So f is bounded. So mod f is bounded, so f is bounded. So we can say f is bounded over this. So Riemann removable singularity, what it says, this theorem says that when f is bounded in a related neighborhood, bounded on the star, which is related neighborhood. So it is bounded, so Riemann removable singularity theorem. This says zero is removable singularity. It is just because if you see this is identity function and we can extend to whole complex plane and it will be still holomorphic. In fact, it is an entire function. Okay. And we can extend this function to whole complex plane. That's why it is removable singularity. Okay. So most of the time what happens, we don't have. So if you remember Schwarz reflection principle, there we were extending our uh, complex function to its reflection about real plane, right? The domain where the domain was symmetric around symmetric about x-axis or real line, and there we were on the upper half it is defined, so we can extend it to the lower half. But here we are extending in one point where one point is missing. So we can define at 0, we can define z is equal to, so fz is equal to 0. So that is why we can extend this function very easily. So we have the second question. So here we have another functions defined on c minus 0. So uh, if you see this function, where is this having problem? This function has problem at 0. When you put z is equal to 0, what happens? E power 0 becomes 1 and it is 1 by 1 minus 1 means 1 by 0 and it is giving us infinity. Value is infinity. So which kind of it is not well defined, of course. So it is a singularity. Which kind of singularity it is, that is what we have to check. So, okay, what can we say? It is bounded or not? When z goes to 0, uh, f is not bounded. I'm saying why? Because let's say limit f, not f, exactly. We can take mod f. Okay, how to deal with this? Right. What about this function? This is not bounded. I will show this. 1 minus e power z. It's continuous function, holomorphic function, whatever you want to say, continuous or holomorphic also. So in a neighborhood, and z is equal to 0 is a 0 of this function. Let's say it is gz, and 0 of g. So z going to 0, where gz goes? Gz goes to 0, right? This implies mod of gz. This also goes to 0. And when you take 1 upon gz modulus, this goes to infinity, right? Now this goes to infinity. This implies modulus of f of z. This goes to infinity. So this is second criteria. So when it is pole, if it is satisfying this condition, right? Z goes to z naught and mod of f goes to infinity. So this is what is happening in this case. So going by step, 1 minus e power z, this is a continuous function. And we also know that when z is equal to 0, this function is becoming 0. So continuity, using continuity, what happens? Whenever z goes to 0, gz should also go to 0. In this step, we are using continuity. Continuity. Okay. And the next step is modulus is also continuous function. So again, modulus property we are using. And this is common thing when something is going to 0, 1 by, for example, 1 by n goes to 0, then n goes to infinity. So this is a basic thing. It's 1 by g is nothing but our z. So that's how we prove. And now it is pole of order m. Okay. In the first case, it was removable singularity. Here it is pole of order m. Okay. So let's see third question. Again, we have a function which is defined on everywhere but one point. It is given by this rational function z square minus 5z plus 6 divided by z minus 2. Determine type of singularity at z is equal to 2. How to determine? So in case of rational function, this is the part. So this is in one variable. so we don't have to think too much. So first, let's factor numerator and denominator and check what happens there. Okay. So in case of polynomial, we have already seen that when our field is complex numbers, we can factorize them into linear factors. So numerator can be factors. So f of z can be written like this: z square minus 5z plus 6 by z minus 2. We can get factors of numerator. They are what they are: z minus 2, z minus 3 divided by z minus 2. Okay. So take g of z is equal to z minus 3. So then we see that c is entire function. And it agrees with f on c minus 2. On c minus 2, fz and gz is to agree. So we can extend this whole function, to whole complex plane. Okay. What can we define at z is equal to 2? Or at z is equal to 2, you can define -1. Right? So it is removable singularity. So we directly checked that it can be extended to whole complex plane. That is why it is a removable singularity. So extended means extended whole, it remains holomorphic. The extension is such that it remains holomorphic when we define at z. Okay, so now fourth question. Here function is defined on c minus 0. So it is zn into e power 1 by z for some positive integer n. We have to check the singularity, type of singularity. So let, let's get Lorentz expansion for f. Lorentz expansion for f. How to deal with this? Fz is equal to z to the power n. So around 0, we have to take all the powers of z. So zn, we are not going to change anything, but e power z, e power 1 by z can be written like this. 1 plus 1 by z plus 1 by 2 factorial into z square plus 1 by 3 factorial into z cube, and so on. So what we see here, if you multiply them inside z to the power n plus z to the power n minus 1 plus and so on, at nth step you get 1 by n factorial plus now 1 by n plus 1 factorial into 1 by z, 1 by n plus 2 factorial into z square, and so on. So there are infinitely many terms of 1 by z, infinitely many non-zero terms of 1 by z, powers of 1 by z. So that's why this shows that f has essential singularity. So, so why I'm using Lorentz expansion version? Directly, you look at this picture. Zn is bounded in unities, right? Z power n. This is bounded function for unities, but e power 1 by z, this is not bounded. Okay, and it is not neither it is bounded, but its image is dense inside C. That is another question. If it is bounded away from 0, or it is its limit is going to infinity, something like that could have happened, but it is not the case. If you take various sequences Zn which are going to let's say 0, then you get different values. Okay, it is not neither removable nor pole. You can prove by this way also. He, uh, it is not removable, first of all, because the limit of function does not exist. So yeah, of course, when it is uh, removable singularity, when we define something, it remains continuous and holomorphic. So this means that uh, so the this is one way the proof. Another way is to show non-removable and not pole. We can show this way. Non-removable, we can check directly. Because this is since limit of function, limit z goes to 0, f of z. This does not exist. This we have to check. And not pole means limit f or mod f, whatever. This is not going to infinity. How? Limit z goes to 0. Okay. We can we can see this way. If we take Zn is equal to Zn is equal to something which is going to 0, what you like, 1 by 2 pi I n. This goes to 0, right? Then what happens to f of Zn? F of Zn is equal to z power n e power 1 by z, Zn, Zn. So 2 pi I n power n. Okay, so this n, the n's are different. Okay, so here let's say it is 10 z, and in the function it is fixed. In the sequence it is varying. Okay, so I'm fixing it. Let's say 10, or in the notation we have to change then zk. Let's say sequence is zk. Let it remain n. Then it is zk everywhere. So 2 pi I k power n into e power 1 upon, when you are putting zk, so you just directly put 2 pi I k, 2 pi I k. And from here, what we say, this is a constant. It is uh, k power n, some c into k power n. This goes to infinity. Okay. So for one thing, what we get, it goes to infinity. We take different sequence. Some it will go somewhere else. Okay. What can we take to prove that? So right, let's make a one thing which is bounded. That will so prove that will prove that. So there was a little mistake. One thing is that this is 1 by z. when we are putting zk is equal to 1 by 2 power I king, right? So this is 1 by this. So it is always 1, it is going to 0, so it is everything is going to 0. So here we have mistake. This goes to 0. Okay. Now we need something which goes to non-zero thing. Okay. How to do that? So here I'm not getting how to do this, but this limit does not exist and the modulus is not going to infinity. Modulus is not going to infinity is clear from here, and why it does not exist is not clear. We can define 0. Yes, if you are using this one sequence, but another sequence, we need another sequence. This this is this is what we are going via y-axis or purely imaginary numbers. What if we go via real numbers? Let's say uh, zk is equal to 1 by k. What happens? Then f of zk, this is z, oh sorry, zk power n means 1 by k power n. It is again going to 0. Into what? E power k. Oh, I see. So we get this number, and it is not going to, actually it is going to infinity. You see why? uh, E power k is exponentially increasing and k power n is increasing polynomially. So there is this expression, if you see, e power x can be written 1 plus x square by 2 factorial and so on, something like that. Then e power x is far more bigger than x power n by n factorial plus and so on, x power n plus 1 n plus 1 factorial and so on, something like this. Then if you divide by x power n from both sides, what happens? E power x by x power n is bigger than equal to x by some factorial things, okay? Some n factorial or n plus 1 factorial, I don't, I think n factorial plus here x power 0, x by n plus 1 factorial and so on, okay? Something like this. So plus something more, everything this is bigger than x by n plus 1 factorial, okay? So when x goes to infinity, what happens? So here I have to write 2 lines. Now this value, when x tends to infinity, what happens to e power x by x power n? this is fixed number. Sorry, bounded. So we check here and use uh, comparison test. Okay. So this goes to infinity since x by n plus 1 factorial. N plus 1 factorial doesn't make much difference because it is just a constant. X goes to infinity. Or we can write x is goes to infinity. So we got two sequences where both are going to 0, but their images are going to, one is going to 0, another is going to infinity. So limit does not exist, this first case. And the second case is, it is not going to infinity. Modulus of f is not going to infinity because one of the its modulus is going to 0. We have already seen. So this way also we can prove it. Okay. So now let's see fifth question. We have a function defined on C minus 2 points, I and minus 3. And it is a rational function of which are we know numerator and some built denominator. Determine type of similarity of z is equal to I. We can directly see from here what we can see. Z is square plus 16. This is an entire function, right? Even if you divide by z plus 3, this function is holomorphic in some neighborhood of on the I, maybe one radius, we can take one. Okay, so if you see from the picture, 3 is somewhere here and I is here. So if you take unit radius ball, it's not well placed. Something like that. Then this function is holomorphic because the singular part for this function is at here. Okay. So this is holomorphic on the I1, this ball. Then let's say this is C of Z. So what we have written, f of Z is equal to C of Z, which is holomorphic on this and is not 0 everywhere on the I1. Okay. And non-zero. This is nothing else. It's just observation. Okay, I'm not going to use that. So this is z minus I to the whole square. This was missing. Now fz is gz divided by z minus I to the whole square. So if you see Lorentz series function for g, it starts from a naught, a1, a2, a3, and so on. Gz has expression, Taylor series expression. It has because negative part there's no negative for this. A naught plus a1z. We are checking at I. So a1z minus I plus a2z minus I to the whole square. There were some coefficient problems. If you write Taylor series extension, then there's no issue. Just like that, we write this gz. Now gz by z minus I to the whole square. From here, you get a naught by z minus I to the whole square plus a1 by z minus I plus a2 plus a3 divide a3 now z minus I and so on. Now positive powers. Sorry, how many powers speaking? a4 z minus I, the whole square plus and so on. Now this part is called singular part, and it has negative power, it's equal to 2. Okay, this 2 gives us whole of order. F has whole of order M. So when Lorentz series expansion starts from minus M, then it has pole of order M. If it has infinitely many negative powers, then it is essential singularity. So this way. Uh, so here in this scenario, we have pole of order. Let's see another question. Uh, hi. Fz and Gz are two non-constant holomorphic functions with zeros of order M and N. So using hypothesis, what we can write? Using factorization theorem, Fz is equal to holomorphic with zeros of order M. Z minus at Z naught. So Z minus Z naught to the power M into Gz, or sorry, F prime Z, or what some notation we have to get Hz. Okay? Some another function, okay, which is now it is non-zero holomorphic function. All the zeros has been counted in this part. H of Z naught is non-zero. In fact, in a neighborhood, H is not vanishing. Okay, not only at Z naught, but it is not vanishing in a neighborhood. H of Z naught is non-zero. How we can write Z? Gz, Z minus Z naught to the power N into H. Is write it H1 and H2. And now H1, or sorry, H2 of Z naught, this is also non-zero because all the zeros has been counted in this part. Right. Now we are going to see options, which options are correct. The Z naught is an isolated singularity of function. But what can you say from here? Fz by Gz. This can be written as Z minus Z naught to the power. So M minus N. I'm directly writing this. You understand from the above expressions. This is H1Z divided by H2Z. And you see H1 and H2 are non-vanishing in the neighborhood. So uh, this is non-vanishing in neighborhood, maybe in D Z naught epsilon. I'm just taking epsilon something, okay, for some epsilon. Holomorphic function. So what can you see from here? Depending on M minus N, what number you can decide it is either 0 or whole. Clear? So it is an isolated singularity, that is clear, because in a neighborhood object, this function is holomorphic. There's no problem. So only problematic part is this, and this gives us, because M minus N is a fixed number, okay? If it is 0, non-zero, or something like that, it decides at Z naught there is singularity, and it is Z naught is isolated singularity. So first option is correct. Now the second option, function f by j has removable singularity at Z naught. If m is bigger than or equal to n. If m is bigger than or equal to n, m minus n is this number is positive or greater than or equal to 0. So z minus z naught to the power m minus 1, m minus n. This is holomorphic, right? So now it is product of two holomorphic functions. This is also holomorphic, this is also holomorphic. So what we get? Fyg is holomorphic in a neighborhood. Okay? That is, you have to understand. We don't know in outside the neighborhood. There may be another zero, another pole, or something like that. So Fyg is holomorphic or by product of two holomorphic functions. Holomorphic. Hence holomorphic. So holomorphic, every time we don't mention the domain, so you understand what it means in some neighborhood. Okay, so in this scenario, this is part B. Part B, it is correct. We can remove the singularity. We are now saying that Fyj is holomorphic function. Correct. Now, for part C, if M is strictly bigger, then what it tells you? Z minus Z naught to the power something, positive power, into some non-vanishing thing. So Z minus Z naught power something that gives us 0. And here it is written 4. So it is wrong. It is wrong. Now, here it should have been 0. Then it was correct. Now, f of g has pole of order n minus m in the scenario when m is less than n. When m is less than n, then n minus m is positive. This implies n minus m is positive number, and that the above f by g, f, this is part B, f by g can be modified by this way. 1 by z, this is equal to 1 by z minus z naught to the power n minus n into some non-vanishing thing, some holomorphic neighborhood. Okay, let me write hz only, which is h1z divided by h2z. This implies z naught is pole of order n minus 1. The option is correct. You have to just think that this hz is well defined. It is not vanishing holomorphic function in a neighborhood. That is how we have chosen in factorization, using factorization theorem. All the zeros have been already counted inside this part, z minus z. Okay, so part B is correct. How about part E? Function fyg has an essential singularity. No, no, it is not essential singularity. Why? It m minus n can be either positive or negative, negative or non-negative. In the negative case, it is whole, and it is positive case, it is removable. Removable we already seen in the part B. It is whole in using part B. This is correct, incorrect. We are just using B part and D part. When it is positive m minus n, it is 0. When it is negative, it is 4. That's the, it is not essential singularity. Okay. Now we have seventh question. Lorentz series expansion of 1 by 1 minus z has a non-zero coefficient with negative indices. So on d minus 0, we know what 1 by 1 minus z. This can be factored as, or this can be this expression for this Taylor series or Lorentz series expansion. There 1 plus z plus z square plus z cube and so on. There's no negative indices. All the indices are positive. See, powers of z are uh, positive, no negative powers. This is no A is wrong. Lorentz series expansion for coincide with power series. Yes, this is what we have already written here. So how we are calculating this? We are just using real analysis, uh, the expansion we have already seen there. Here in this case, when modulus of z is less than or equal to 1, or when it belongs to D, what happens? We see that this power series converges absolutely and uniformly in any neighborhood or any compact set which is contained inside unities. So, and that agrees with this on real numbers part or on open interval 0 to 1. So these two series, or they're in complex or real, doesn't matter. They're same. Okay. Now what our question says, another way is to calculate all the coefficients. I don't think that is difficult. An can be calculated by some integral of f uh, fz dz over circle over unit circle 1 upon 2 pi I here. And anything else? Here it is z plus z power. We are calculating at 0, so z power n. Series is centered at 0, so z power n plus 1. Right. So what is f here? F is this. This is our fz. Calculate its nth derivative. All the derivatives you can calculate, and they will turn out this is n factorial. So you will see that ans you will get one. Use Cauchy integral formulas to calculate them. Okay, right. So we get part C, correct. Part D. So this was part. Now part C. On a annulus z is strictly bigger than 1, complement of closed unities. Function 1 by 1 minus z has Lorentz series expansion where all the coefficients are -1. Okay, let's see. So there's some mistake here, okay? There might be, they're talking about negative powers. Oh, okay, okay. So indices may already cover this, no problem. N is already, they're all negatives. So I thought, okay, let's see how to do this. We are given mod z is bigger than 1. So we can see from here 1 by mod z is less than 1. We somehow use the same formula which already we have for mod z when mod z is less than equal to 1. When mod z is less than 1. So we make changes according to our need, just like that. 1 by 1 minus z, this can be written as, we can take z common or minus z common. Let's take minus z common. Then 1 minus 1 by z. When you product this minus z inside, you get minus z1, minus z and plus 1. Okay, fine. Now we are fine. This is equal to 1 by minus z into 1 by 1 minus 1 by z. Now this 1 by z, this has modulus less than 1. Use this. So what we get here, fz, when mod z is bigger than 1, fz is equal to 1 by minus z into this series 1 plus 1 by z plus 1 by z square. Now we are taking same series, but not in z, but 1 by z. 1 by z, 3, so on. Multiply by minus z, 1 by minus z inside. So it becomes minus 1 by z minus 1 by z square minus everywhere minus 1 by z cube. Because of this minus, this is what it is. So we can directly write in summation format. Z power n. So when we take negative ones, n from minus 1 to infinity, minus infinity. So there's no problem. All the powers has been all negative, but coefficient we have to write minus here. Okay. So what was our question? Fz has Lorentz series expansion this way, right? This is correct. This is what we get. So the third option is correct. So calculating coefficient in Lorentz series expansion is difficult. In this scenario, it is easy, okay? Because we know the expression for 1 by 1 minus z when mod z is less than 1. So we are using that. That's why we are directly writing. Usually it is difficult, okay? Okay. Lorentz series expansion or 1 by 1 minus z is unique, has unique coefficient irrespective of the annulus centered at 0, where the Lorentz series expansion has been considered. Sorry, this is wrong. Why? We are using B and C. They have different coefficients, different expression, different annulus. So when mod is less than 1 or bigger than 1, they're different. We are using B and C. The coefficients are different. So let's see. Last question. It's this is last question, right? Consider a function from c minus 0 to c minus t closure, which is holomorphic on c minus 0. So can we extend this function? Something like this. We have to answer this question. So first of all, 0 is not essential singularity. Why? It's not essential singularity because image is not dense. Image is going to c minus t closure. and D closure contains many open sets. So image is not intersecting many open sets. So image is not dense. So it means using Pesaro-Weierstrass theorem that F is having not essential singularity at zero. So essential singularity part is over. The first question is essential singularity. This is wrong. This is what I was explaining. Why? So first A part, I explained this way that Casorotti Weierstrass theorem says that image F of any neighborhood, in fact, okay, image of any neighborhood or neighborhood star, I'm writing, means neighborhood minus deleted neighborhood, okay, minus zero is missing there. Any neighborhood is dense. In C, this is the theorem, Casorotti-Weierstrass theorem. But we see that image is going to C minus D. We see that image is going to C minus D path. So it fails. Image in this scenario, in this question, image is not dense. Whole image is not dense, or image of all domain C minus zero is not dense. So first is over. This is wrong. Now what about second? Function 1 by f, we have to consider 1 by f. It has a removable singularity at that point. Okay, let's see. So we know that by hypothesis, mod of f z, mod of f z I should write. For any z it is working. It is bigger than 1. Because they are not in unit disk. You see from here? So the modulus of f is bigger than 1. This implies mod of 1 by z fz. This is less than. Now we are going to use Riemann removable singularity. Riemann removable singularity theorem. What it says? It says that function is bounded in a neighborhood of singularity, then we can remove the singularity. So here it is bounded everywhere. Everywhere means z varying over all complex plane minus 0 mod of 1 by fz is bounded by 1. So we have 1 by f as removable singularity at 0. Or in fact, all the singularities of 1 by f are removable at means wherever they are in the domain. Okay, because 1 by f is bounded. That's all we are going to use. Fine. Now this is fine. The next question is, so once 1 by f is having removable singularity, so all of its removable singularity, wherever the singularities are, they are all removable because 1 by f is bounded. 1 by f is bounded. So 1 by f can be extended to a holomorphic function, which is entire, because wherever removable singularity, we can remove them. So this implies 1 by f can be extended to an entire function. Okay, why? Because 1 by f, the modulus is bounded always. This is for every z. Okay, so in the domain, of course, c minus 0. So for 0, we don't care. Wherever singularities are, there are removable singularities. We can remove them and make it entire function. Once it is entire function, and this is also bounded function, we are going to use Liouville's theorem. Uh, what it says, 1 by f is constant. Function 1 by f is constant. Now, so 1 by f is constant, so f is also constant. So that's all, non-zero constant. So if it was 0, so it was never 0. You see from how can it be non-zero constant? Non-zero part we have to think about a little bit. Why it is non-zero? 1 by f is constant. Means 1 by f is 1 by f could be 0 also. But in that case, what will be f? F is not defined anywhere. F is infinity everywhere. This is wrong. So that is why f should be no. F is constant function. 1 by f is constant, non-zero constant function. Okay. That is, I think, clear from here. Otherwise, if 1 by f and f both are well defined, then and one is 0, then other should be infinity, and that is not defined, well defined function. Okay. Non-zero constant function. Right. So now we have two more options to check. Function 1 by f when it says at 0. So we have to check 1 by f of 0 is 0 or not. Function f cannot have pole at 0. Okay, wait a minute. We are going to use part C everywhere. So part C implies here. This is correct. Cannot have pole. So because it is entire function, once it is non-zero constant function, it is entire function. So it cannot have pole at 0, right? Or how about part D? Function 1 by f. When is a at 0? No, of course not. So fz is equal to c for every z in C. Once it is constant, we can. So actually, we have extended our functions to an entire function. Right? We got f. F has this property that 1 by f was constant. We have checked, and it was entire. So we checked for 1 by f to be constant. So f has to be constant, and it is non-zero that we already calculated. So fz is equal to that constant function. It was defined initially at c minus 0, but now it is an entire function defined everywhere on complex plane. So we're going to use, and it is non-zero. Once it is non-zero, when it's a test, doesn't make sense. It is wrong. Okay. Part C again says non-zero. Part C. We use that and conclude that 1 by f vanishes nowhere because it is non-zero constant function. as well as f as well as 1 by f. They both are non-zero and constant functions. Okay, I hope it is fine. If you have any doubt, you can leave your comment. When I will be free, I will be able to reply to comments. Okay, uh, I will now request, maybe this first time requesting to you, subscribe my channel and make your friends, convince them that this is going to helpful for them. So in future, if you like uh, my videos, if you want to hear something or some topic to discuss, uh, we'll discuss that. Okay. So subscribe my channel, like my videos. Thank you. Bye bye for today. We'll meet again next week, Saturday at the same time. Please join. Uh, the link and everything is given to you by all. So at 4 p.m. Saturday next week.